Hello everyone. I'm trying to see if this is working and using a tablet to look at the book and or do the homework and then record the video for you. Okay, so before we look at the homework, I would like to introduce the definitions and explain some theorem probably which help you understand the materials better. So the second chapter is probability. The probability is the very important chapter and definition in the statistics. Okay. So first the section is a sample space. Sample space, before I introduce sample space, we would like to look at the definition. The set of, okay, so it's not working. Let me see if it's working here. Okay. So the sample space is the set of all outcome of a statistical experiment is called a sample space. Sample space is basically means all the possible outcomes. For example, if you flip a coin, you're going to have two options, two possible outcomes, head or tail. Okay, and if you roll a die, it's going to be you have six sides, so all the possible outcomes are 1, 2, 3, 4, 5, 6. Okay, 6 points. And if we're only interested in whether the number is even or odd, you can see the sample space of even is going to be 2, 4, 6. Okay, and we use a set. Okay, a set like a set. We use a set S. Set is a S. That's why we use S. S is a set of head and tail. So this is the first way to express a sample space. The second way is you can use a tree diagram. What's the meaning of a tree diagram is you can list all the possible outcomes. Okay, so let's look at example might be good is, okay, let's look at this one. Oh, this is not a tree diagram. Okay, it's right here. Suppose that 3 items are selected at random from a manufacturing process. Each item is inspected and classified defective D or non-defective M. To list the elements of sample space provided by the most information, we construct the trigram or figure the trigram for the sample space. Now we have, if we select the 3, starting with the first path, we get sample point indicating the possibility that all 3 items inspected are defective. As we proceed along the other path, we see that a sample space. So you basically have DDD means all 3 are defective. DDN is 2 defective and 1 non-defective. While the third one non-defective. Then the first one defective, the second one non-defective, the third one defective, or the first one defective, the second and third one non-defective. So basically, you're going to have all the possible combinations. 1, 2, 3, 4, 5, 6, 7, 8. So that's all the possibilities. Well, when you say if you have 2 child, like for example, if we say a woman have, like a family have 2 children, well, the possibilities before we know the gender of their children, it could be 2 boys, boy girl, girl boy, or girl girl. You have 4 possibilities. So it's pretty much all the possibilities. Now look at this one. The first one item could be defective and then not defective. The second one could be defective and not defective. The third one can be defective. So after the second one, you have 2 options. After non-defective, you could also have 2 options. So together is defective, defective, defective. You can have DDD, and defective, not defective. So DDM. So that's the exact same thing. Use tree diagram or you use a sample space. Just list them out. Okay. So that's the first one is a sample space. Basically is a way to express all the possibilities or all the outcomes, a mathematical way to explain that. The second section is event. Okay, an event is a subset of a sample space. Okay, A subset. Subset is kind of like a sub. Sub means one part. Okay, the kind of one part of a sample space. Okay, subset of a sample space. For example, if we say if you flip a coin and then you have two outcomes and either head or tail, then if we say S equals H, just the head is a subspace of a of the space. Let's say this is a subspace of S. Okay, the H head is just a subspace of head and tail. Okay, now we look at the event. For example, if we flip a coin, the event could be just a head. Okay, so we probably can say, oh, the probability of an event is the probability of a head. For example, the probability of you flip a coin, the probability that you will get a head is what? Is 1/2, right? So then the probability of a head is, well, when we do the probability, we don't use that. Sorry, we do the probability, we don't use that anymore. So we use probability of head is 1/2. So then this is the event. Well, the event is a subset of the sample space. Well, if we put all of them here, it's just all this. All this. If we put a head and tail here, it's going to be 1. You can, if you put all the sample space in, so head or tail is going to be 1, because you will be either get head or either get tail, right? Okay. So the event is kind of like something we mentioned. It's one possibility of a sample space. For example, the weather tomorrow could be sunshine day, could be raining day, could be a snowing day. So that's the sample space of the weather. Let's say we only have 3 conditions, not mentioning that not mentioning the other weather like a cloudy day, whatever. Okay. So now suppose our sample space is snowing day or sunny day or a rainy day. So now we can say the event is one of these 3. So probability of tomorrow is raining. So that tomorrow raining is an event. Okay. Okay, let's continue. A complement of an event A with respect to S is the subset of all elements of S that are not in A. Okay, a complement of A is the respect to S is kind of like another way, a complement, complement. So, for example, if you see the event A, we'll still take this one example. If the event A is head, well, not head should be what? Should be tail. So the complement set of A is tail for this one. Okay. So basically, the complement of event A with respect to S is subset of elements of A not in A. That's right. Yeah. Let's look at that. Give another one, a new page. Okay. For example, if my sample space is 1, 2, 3, 4, 5. Okay. If we have A, the space, or event A is 1, 2. Now the complement of the event A or the set of A, complement set or complement of event is going to be 3, 4, 5. Okay, I think that makes sense. Let's make more sense. Okay, that's the complement set. The intersection of 2 events A and B, denoted by A intersect B is the event containing all elements that common to A and B. Let's look at the example. Basically, it means you find the common elements. So suppose A equals 1, 2, 3, 4. Okay. So suppose the set B equals 3, 4, 5, 7. Now, if we want to look at the intersection of A and B, so A intersect B is going to be the common elements. So common element is going to be 3 and 4, 3 and 4. These are the common. So the elements in common. So 3 and 4 A intersects B is going to be 3 and 4. So the intersection of even A and B here is going to be 3 and 4. It means contains all elements that are common to A and B. Okay, so the union of two events A and B is going to be all of them together. So here, still take this as example. So A union B so is equal 1, 2, 3, 4, 5, 7. Okay, so you have 1, 2, 3, 4. 3, 4 is already here. In the set, you won't write those elements again. And that's 5 and 7. So this is A union B. So basically put A and B together. Okay. That's okay. There is a you may want to look at this example. Now this one. There is an example. We can take the example in your homework later. Look at the homework if we have an example. Okay. The section 2.3 counting sample points. Okay. The first one is multiplication rule. If an operation can be performed in n1 ways, and if for each of these ways a second option can be made performed in n2 ways, then the two options can be performed in together in n1 multiplied by n2 ways. Okay, let's look at an example. How many sample points are there in sample space when a pair of dice is thrown once? If you're throwing once, a pair of the dice. So the first pair will have the first die is 6 points. The second one have 6 ways. The second one also have 6 ways, 6 different outcomes. Together there will be 36 outcomes. It's going to be the first one could be 1, 6, okay, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. Well, then continue. The first then. Oh my bad. I should say 1, 6. It should start from 1, 1, 1, 1, 1, 2, 1, 3, 1, 4. Okay, 1, 5. 1, 6. So you see you have 6 outcomes here. Let me take off this. And then start from 2, 2, 1, 2, 2, 2, 3, 2, 4, and 2, 5, and 2, 6. If you continue with 3, 3, 1, continue, you're going to have 36 possible ways. Okay. If a 22-member club needs elect a chair and a treasurer, how many different ways can these two be enacted? Okay, so you have 22 members. Okay, then you elect a chair. So either one of these 22, either one of the 22 can be enacted as a chair. So let's, for example, 1, 2, 3, 4 until 22. Let's say all of them have a number, okay, representing these people. So either one of them can be the chair. Now, we elect a chair. Suppose we select one from them, then we're going to have 22 possible ways, okay, since we have 22 people here, either one of them, so there will be 22 ways. Once this person is chosen, we only have 21 people left, so we have 21 times 22 ways be elected. Suppose there one person can be only one position. Okay. So that's the multiplication rules. If operation can be performed in N1, then second operation is N2, then third option is N3, then continue, you just multiply all the possible ways together. Okay. So a permutation is a arrangement of all or part of set of objects. So I would like to also introduce a definition to you. Is called factorial. Okay, so n factorial equals n times n minus 1 times n minus 2 times continue. Every time you reduce one number, okay, so it's until 1. For example, 3 factorial is going to be 3 times 2 times 1 equals 6. And if we say 4 factorial equals 4 times 3 times 2 times 1, well, equals 24. So that's how you calculate factorial. And 0 factorial is special case is equal 1. The number of permutations of n objects is n factorial. Okay, and the second theorem is the number of permutations of n distinct objects taken R at the time is taken R from n distinct objects is n factorial over n minus r factorial. For example, in 1 year, 3 awards research teaching service will be given to a class of 25 graduate students in a statistics department. If each student can receive at most 1 award, how many possible selections are there? So, well, you take the previous example, like to select a chair or the other position. So basically, the first one you have 25 people, 25 graduate students. So whatever award you want to give them, so you have 25 options. But once that award is given out, it says each student can receive at most 1. So you only have 24 students left because that one has been awarded with 1 award. Okay, has been given 1 award. So you only have 24 people left. So then you have 24 options to present the second award. So it's 24. After the first 2 being selected, those only 23 graduate students remain for the third award. So you have 23 options. To get 24 times 25, 24 times 20, so 25 times 24 times 23. Okay, and then this is, if we use that theorem, we use 25. You can use 25 factorial over 22 factorial. Basically, what's the meaning of that? Is P325 equals, what's the meaning of that? The meaning of that is 25 times 24 times 23 times continue multiplied by 1, and you have 22 multiplied by 21 and continue multiplied by 1. So everything else will cancel out. You only have 25 times 24 times 23. Okay, so that's the same idea as this example. I would like you to look at the example 2.19 by yourself. If you have a question, you can ask me. I think it should be the same idea. Okay. We will look at the homework later. Then theorem 2.3, the number of permutations of an object arranged in a circle is n minus 1 factorial. Basically, it's the last one. You arrange in a circle. Basically, your last one is taken out. For example, let me see. Arrange in a circle. The circle actually takes 1 option away. Let's look at the example. We have a considered permutation of distinct objects. That is, all objects were completely different or distinguishable. Obvious, if letters B and C are both equal to X, then 6 permutation of letters A, B, C become AXS only have 3, which only 3 are distinct because 2 of them are the same. Okay, so this is therefore with 3 letters 2 being the same, so you have taken out that 2 same options away. So it's 3 factorial over 2 factorial equals 3. Okay, so let's look at the theorem 2.4. The number of distinct permutations of n things of which n1 are of one kind, n2 of second kind, nk of the kth kind. So basically, they are not all distinct. They are not different. They are not all different. Okay, some of them the same. They have several things. The first n things are one kind, n2 things are one kind. So basically, they're the same. Okay, so we have to divide out those same kind options. Let's look at this example. In a college football training session, the defensive coordinator needs to have 10 players standing in a row. Among these 10 players, there are 1 freshman, 2 sophomores, 4 juniors, and 3 seniors. How many different ways can they be arranged in a row if only their classes level will be distinguished? So if their class level distinguished, we can tell that 2 sophomores in second level, 4 junior third year, 3 senior third year. So you will only say class levels. So we have we have 4 class levels. We're not distinguished by names, but by class levels. So the first, all of the combination is 10 factorial. But the first one will have 1 freshman. As 2 sophomores will be 2 factorial for those two people combinations. And 4 juniors together have 4 factorial combinations. 3 seniors is 3 different seniors. They have 3 combinations. So we have to divide out those common combinations. Okay. And let's look at the next one. The number of combinations of n distinct objects take R at a time, which is select R from M. This kind of selected. Okay, selection. This is different from permutation. It's called combinations. For example, a young boy asks his mother to give 5 Game Boy cartridges from his collection of 10 arcade or five sports games. How many ways are there that his mother can get 3 arcade and 2 sports games? So basically, you have 10. Okay, you choose 10. So first one, the first number we selecting 3 cartridges from 10. So select 3 from 10 is choose 3. So normally we say choose 3 from 10. That's what we write. Okay, so it's going to be 10 factorial over 3 factorial times 7 factorial. That's the definition of select 3 from 10 or select R from M. Well, you can use your calculator to do 10 factorial over 3 factorial multiplied by 7 factorial. Or you can do that. 10 times 9 times 8. You choose 3 number from the top. And the 3 number in the bottom as well, but just from 3 and times 2 times 1. They are exactly the same. Okay, then they have 120. Okay, again, 3 numbers from 10, okay, down 1 each time. And then 3 numbers from 3 to 1. So then cancel, I got 120. It's the same idea as this. These are exactly the same. But if you have a calculator, the calculator can do 10 factorial divided by 3 factorial divided by 7 factorial, okay? And then the second one, they can select from 2 from 5. Together, it would be, so you choose the first one, choose the 3 from 10. Then you choose 2 from 5. So that's all your options. Together is going to be 120 times 10 equals 1200 ways. Okay? Then 2.4 is probability of an event. Now let's look at the probability of event. Actually, in this book, I think all the probability of event are given not really very hard, but it's kind of like introduction of the probability. It does not have a lot of difficult probabilities at this chapter. So the probability of event is the sum of weights of all sample points in A. So therefore, the probability can be at most 100%. Okay, if it's for sure happen, it's 100%. If it never happen, it's going to be 0. Well, sometimes you say most likely happen, we would say 8%, 90% is most likely happen. So it's going to be, the probability will be from 0 to 1. Okay, from 0 to 1. I don't know why I cannot use that pen. Those are not available. Okay, so I think I did use that one before, but I'll check it later. Okay, so the probability is always bigger than equal to 0 or less than equal to 1. It can never be bigger than 1. Okay, the empty side, so the event never happened, is 0. Well, PS is for sure the thing will happen, or all the sample space together will be equal to 1. Okay. If A1, A2, A3 are subsequence or sequence of mutually exclusive even, which means A1 and A2 don't have anything in common. For example, tomorrow is either going to be sunny day, rainy day, or snowing day. So we just consider three options. So if tomorrow, the probability of tomorrow either snowing or sunny or rainy day is together is because they are all different. They are not mutually common in any part in common. So all of them, you add all the probability together equals 1. So that's the meaning of that. Okay. Let's look at this one. A coin is tossed twice. What is the probability that at least one head occurs? One head, it could be head, and head, tail. The second one, head, or, okay. That's all the three options. And at least one head occurs. Head, tail, head. Well, the last one is tail, is there's no head. So the probability is going to be 3 out of 4. So probability equals 3 out of 4 because all the possibility out of the sample space is head, tail, head, tail. So you have two options, two possibilities, but 3 out of them is at least one head occurs. So the probability is 4 over 3. Okay. If an experiment can result in any n1 different equal like outcomes, and if exactly n of these outcomes correspond to even n, then the probability of even a is probability of a equals n over n. Okay, let's look at this example. This is an interesting example. In a poker hand consisting of 5 cards, find the probability that 2 holding aces and 3 jacks. Okay, so you have 5 cards. Okay, 5 cards. When you have 5 cards, you want to say the probability of a pair, probability of a string, a probability of a snake. Like when you play the Texas cards, you know that. Okay, so now if you have holding 2 aces and 3 jacks, the probability of that. So how many? So first, when you do the probability is always the probability is what? According to definition, is n over n. Okay, so it's small n over bigger n. So first, we randomly select 5 from 52. The probability is going to be all the possible combinations. Selected 5 from 52. That's your denominator, all the possible outcomes. Randomly select 5 from 52. Now, we are going to have 2 aces. That's the even we require. So 2 aces. How many aces do we have? 4. So we selected 2 from 4. We don't know which 2. It doesn't matter. We just need 2 aces. But 2 are selected from 4 aces. Now, then 3. So we have how many jacks? So we have 3 jacks. So, sorry, in total we have 4 jacks, but we only have 3 in hand. So we select 3 from 4. Okay, so that's going to be your probability of the hand of 5 cards, and the probability of holding 2 aces and 3 jacks. That is the probability of that, and then you find that the top is 24. The bottom, you can use the formula to do that, and you get is 2598960, which is 0.9 times 10 to the power negative 5. Okay. I think I will stop here today. I'll continue tomorrow. Then we are going to look at the homework. I hope you're going to spend time to read your textbook. Okay. It's really important for you to understand the textbook. Let me say how I'm going to upload that.